takes care of the positive voltage regulator. Okay, this is only AC to AC converter. The bridge is AC to DC converter, and the capacitor is the storage for the DC. It will contain a constant voltage with, of course, some kind of a ripple. So what you will see over there will be time versus the time. Generally, a waveform which will contain a maximum and a minimum. Peak to peak there will be called VR, ripple voltage, ripple. And if the line is a 60 hertz line, the ripple frequency will be 120 hertz. It will be twice, because these diodes, each one, adjacent one, will charge in 1/2 of the cycle. So as the sine wave, for example, becomes positive,
I bet him.
plus minus, this pertains to the polarity across the transformer, the AC, basically. Once it gets to plus and the minus, the current will go through the upper diode and will return through the adjacent diode, the diagonal adjacent, and it will return back to the power supply. So the current will go out of the power supply, out of the secondary, into the diode, through the capacitor, will go to the ground. Through the ground loop, it will come back through this diode, and then it will return to the AC source. So that will be the return into the AC source. Next, when the cycle goes into its second half, this side will become positive, that side will become negative of the sinusoidal. It's an alternating. Then the current will move through that diode, will go through the capacitor, will go through the ground, and it will return through the top diode back into the AC source. So for the red ones, those two diodes will conduct. For the blue one, when this side of the secondary is positive with respect to the other, as they change every half cycle, those two diodes will conduct. This will conduct forward, will pump through the capacitor, exit through the capacitor, through the ground, will come back here, will come back through that diode will return back to the excuse me, transformer. So that explains how the bridge rectifier is working and is producing double the frequency that exists from the secondary. So if secondary has a full period of 60 times per second, you have 120 plus minus alternation between the 2 points. Therefore, it will produce a 120 hertz ripple voltage across the capacitor, which will be nearly steady. General rule is a ripple voltage on a capacitor compared to the average voltage should be small. So let me see VO average here. VO average is the mean voltage building across the capacitor. Ripple magnitude shouldn't exceed more than 10%. So if you have 10 volt DC on average across the capacitor, your ripple can be 1 volt peak to peak. So it can go to 10.5, sink to 9.5, back to 10.5, 9.5, leaving a mean value of approximately 10 volt. So percentage of ripple should be small. What happens if the ripple is large? It is undesirable because somehow it is going to show itself in the final output. By a small amount, but still it will show. So you don't want to generate a a voltage, a source voltage for a circuit that already contains contaminated sine wave. Well, it's not a sine wave, but a kind of a periodic wave. You will hear it in the circuit if it is an amplifier. So this part completes the AC to DC conversion. A capacitor, bridge rectifier, and that is the popular one. You can do this with a single diode, but then in a single diode you will get 160 hertz ripple frequency, and generally the discharge phase will be longer, and you will require a larger capacitor to keep the ripple to the same size. So it is always preferred, most of the time it's preferred, to use a bridge rectifier. The only disadvantage over the bridge rectifier is the following: that whenever the secondary voltage peaks, it gets to the peak of the sine wave, the voltage that comes at the output, VO peak, will be equal to VP minus twice of VD, 2 diode voltage. So the reason is, if you have a peak voltage across the secondary VP, if you write the Kirchhoff law, you will find that the voltage is up to VP, then it drops by 1 diode voltage, then you get the output, which is the output peak, and then it drops again when it is returning with the adjacent diode. So it drops twice with the diode voltage, about 0.6 of a volt, 0.7 of a volt. So you lose about 1.4 volt, 2 times 0.7, 1.4, off of the secondary winding potential. Sometimes it is significant. That loss is significant, especially if the secondary voltage is a small one, like 4 volt peak, say. 4 volt peak is really not suitable, because 4 volt peak, you're losing 1.7 for the diodes. That's a big loss. But if the secondary voltage is like 15 volt peak, 17 volt peak, losing 1.4, it's a small quantity. It's like 8%, 10%. Okay, so this is the AC to DC conversion. Now the pre-regulator. Yeah, you have a question? Please ask.
Yes, I want to know, VP, is it the voltage across the inductor?
Yes. VP is the peak voltage of the secondary. Okay. Inductor, yes. It is peak voltage. Because the inductor voltage here, I will just show it to you. If you call it Vs of t, secondary, as a function of time, Vs of t is a sine wave, etc., which reaches a Vp and a minus Vp. But when it gets positive, the red ones, the top diode will conduct, it will charge the capacitor to Vp minus twice of Vb, and when it goes negative, this one is the blue one that I marked, so this side becomes positive with respect to that, or you can say this side becomes negative with respect to that side, then it will charge at the peak point at the lower D. So it will charge twice within the one complete period. The half period with the positive cycles, the second half it will charge with the negative cycles, when this side becomes negative with respect to that. So they keep alternating. Now, this is said about the AC into a DC conversion. Pre-regulator. Pre-regulator is nothing but a resistor with a Zener diode. So what's the function of that one? We call this RS. RS, the series resistance. And That one is the VZ. V sub Z, that's the Zener voltage. Okay, if the average voltage here on this side exceeds the Zener voltage, then a current will flow through the RS. So we are going to get a current. It's called I called it IS. On condition that VO average, VO average is greater than VZ. For example, if I put a 5 volt Zener voltage here, and my VO average is fluctuating between, say, 9.5 to 10.5, of course, 9.5 or 10.5, both are greater than the 5 volt. So this potential is higher than that potential. The current will flow in the direction of the arrow. All of that will sink into the Zener. So let's see what is the Zener doing. This is a quick Zener review. My diode, Zener diode, and this is the V diode. This is the characteristic of the Zener diode with the regular convention. And we take this side as the VD. We always define anode as the positive. So the diode that is connected this way, it's connected this way, we are imposing a positive potential on the cathode. So we are using in the backward, in the reverse region in here. Forget about these parts, concentrate only on that part. If the average voltage there exceeds the Zener, the current will flow through the arc. And we can very easily calculate how much is that IS. There, IS will be equal to VO average minus VZ divided by RS. And we can control the size of that current with the choice of the RS. We can easily control how much we want. Now, that current will go entirely through the Zener. Here. IS. Okay. Why it is drawn in the negative region? But take it as a positive number because of the flipping that it took place. It took place right there. So the value of IS can be predicted with that equation very simply. It's the difference between here and there is the voltage drop on the RS divided by resistance gives you the current. So all of that current will flow through the Zener, and we will get a Zener voltage right there. Now, if this line happens to be completely vertical, as ideal Zener, here, there would be no worries. Ideal Zener. If it was an ideal Zener, no matter how much is the current in the Zener diode, you would always see a constant voltage across the Zener. Because if you move IS up here or down here, if you project on the green line, you will read the same voltage. That is called ideal Zener diode. But generally, the Zener diodes have to have this kind of steep, but with some finite slope, which speaks of a Zener resistance. So diodes, generally Zener diodes, they tend to have some kind of a dynamic resistance. Dynamic resistance of the diode is here, RC, as dynamic Zener resistance is equal to 1 over slope. 1 over slope of that blue line. So it is like this. You need to calculate that slope from the characteristic, or often just manufacturer will specify what is their typical Zener resistance. For example, they will say Zener resistance is typically 5 ohm, 4 ohm. It is usually very low, but it can be even 10 ohm or 15 ohm. It's possible. So we get some kind of a effect that if the current changes in that resistor, current moves up and down. If you're going on that slope, you will notice that your voltage across that diode, that reverse voltage, should change by a small amount. Delta of IS multiplied by RZ will give you the change in the VZ. So you can say here, delta of VZ is going to be RZ multiplied by delta of IS. By delta, it means the changing current. So the current is likely to change. Why? Ripple is one of them. So if my ripple is changing from 9.5 to 10.5, the peak-to-peak ripple is 1 volt. So multiply the 1 volt by divide by that 1 volt by the RS, you will get delta of IS. Because here, if you consider the changes in here, delta of IS, if VO is a constant, if you differentiate that basically, delta IS will be constant, doesn't have any change, so it will be minus delta VZ over RS, or delta VZ is just RS times delta IS. So if the current increases in RS, the Zener voltage will increase by change of the current multiplied by RC. We are going to see, therefore, a ripple voltage definitely across the Zener diode. What is the size of the Zener voltage? That the ripple voltage on the Zener is going to be much smaller than the ripple voltage at the capacitor. In fact, delta VZ is going to be RC over RS plus RC voltage divider multiplied by VR. This is the ripple voltage at the capacitor, which is the change. This is the change. So ripple at the capacitor will translate down to another ripple on the Zener, which usually is much smaller than the ripple itself. Look at the voltage divider. You know what you can use? You can use the small signal equivalent. Remember, we had a DC equivalent circuit and then we had AC equivalent circuit. The AC equivalent circuit of the Zener is nothing but the Zener resistance. You don't see the constants. You don't see that average Zener voltage. You see only the change on that. So, change in the Zener voltage will be RZ over RS plus RZ times VR. So if I had 1 volt peak to peak, 5 ohm, RS was, say, 200 ohm, 5. Look how much the ripple voltage will reduce on the Zener diode. 5 over 200. 200 is, let's say, this is the RS, 200 ohm. So we can see that 5 over 200, that's only 2%, 2.5% of the ripple. So your Zener diode managed to reduce the ripple, the capacitor ripple, considerably by virtue of that Zener resistance. steepness of that slope. The steeper is that slope, the smaller is RZ. The smaller is RZ, the better it will kill the fluctuation over there. Because the fluctuation along the green line on the current is not going to change the voltage that much. It all depends how steep is your current. So somebody, when it is designing the value of RS, you should keep that one in your head, in your mind. I should keep RS large. Let's see why large. Comparison to RC. I should keep it large. For example, if my RC is 5 ohm, I want to select that one 200 ohm because it's a considerable attenuation, 5 to 200. So it drops considerably. But if the Zener resistance is, say, 5 ohm, and you select this one 10 ohm, you are not reducing the ripple here that much. You get a lot of current in the RS, in the Zener, but you are not reducing the change. Okay, so RS should be chosen wisely. But here is the problem. Why we don't select RS very, very large? Why don't we select 1 kilo ohm? Let's take a look at that. If I select this 1 kilo ohm, from the ripple perspective, it will look great. Because here, instead of 200, the ripple will be attenuated 5 to 1,000. Well, that's really, really half a percent of the 1 volt, which is super. Actually, 0.5% of the ripple at the capacity. So the larger is RS, the better it will reduce the ripple. But here comes the problem. It comes the problem when you have a load. You want to draw some current from this node. Then what? Let us say I put just some random numbers over there. The problem is completely solved in here, but let me put some random numbers. Let us say we plan and we set IS to 25 milliamp. 25 milliamp. Okay, this is the IS. And we decide to take some kind of a current. Load. There is a current going in here, IZ. The Zener current won't be identical to the IS because as the current comes in, assuming Zener voltage is approximately a constant, the current comes in, it will split into 2 parts. Part of it will go through the Zener, the other part will go towards your load. Fine. But the trick is that you want to stay deep into the Zener region. In other words, the limit to my maximum load current, IL max, here, IL maximum, will be equal to less than 25 milliamp. Why? Why my current at the load is now limited? I can't arbitrarily take 30 milliamp, 40 milliamp into this load and hoping that I will still have the benefit of Zener regulated voltage. The reason is, if the Zener voltage, say, is 5 volts, and you put 50 ohm in here, 50 ohm, 5 volt over 50 ohm will already take 100 milliamp. So tell me, how is it possible that you get 25 here, 100 exceeding there to the load, and yet you still have some positive IZ so that you can keep yourself in the vertical region of that characteristic? You cannot do that. You see, because the current has to stay, this IC has to stay positive. In other words, in reality, with respect to that characteristic, as negative. Usually this threshold is about 5 milliampere. They say, look, if you're going to steal from the source current with that load, allow some current to flow in the zener. In other words, allow yourself to come up all the way to here, to the 5 milliamp. Don't deplete the current that is intended for the zener, to keep it deep into the zener region. Don't bring it to zero. Because if you did that, you will get into the deregulated portion of the zener. In other words, if I put a very low resistance in comparison to RS, then I will be operating here, which means the zener will be like open circuit, it's infinity, because the slope is 0, 1 over 0 will be infinity. So the zener resistance will be like infinity if I overload the zener. So let's see how we're going to choose. On one hand, I want to have current capability for the load, so I can take more than 20 milliamp in here. 50, 60, 70, 100 milliamp, I want to take it. But you cannot do that with one single zener. Unless you know what you do, you make this current 125 milliamp, for example. Well, if you did, you make this current 125, then you've got to reduce RS. But if you reduce RS, this is what will happen here. If you reduce this resistance, then your ripple will increase on the zener path. So, on one hand, we have to keep that ripple voltage very little on the zener by selecting reasonably large. And on the other hand, we want to draw a desired amount of current, and we can't do it straight from the zener. So what's the solution for that? Here comes the buffered voltage regulator, which is more like a realistic voltage regulator. It is a legitimate power supply, basically. That is a transistor. So, if you're demanding a load current that apparently exceeds the limit that you have set in the RS, let us use a buffer, a transistor. Think of it like an emitter follower. No, we haven't covered emitter followers yet. Well, just a transistor. Let's see what we can do with that transistor. If I post it right here. I'll connect the collector directly. Then I will introduce my load here. Okay. You will have IE, emitter current, as your load current, because it's fed from the emitter side. The collector current will be nearly equal to the emitter current. So IC will be approximately equal to IE. Okay? We know that transistors give a constant VBE. What? It is not really constant, but if the VBE is changed by 25 millivolt only, the current in the collector will triple. So if a VBE changes by 50 millivolt, the collector current can change by 9 times. So if a load current in this branch changes by a factor of 9 times, IC will change 9 times at the cost of VBE increasing by 25 millivolts. Where am I computing those 25 millivolts? Remember, the current in a transistor was IC approximately IS times e to the power VBE over VT. So VBEs are 700 millivolt on average, right? But think about what's the difference between 700 millivolt and 750 millivolt. The difference is 750 versus the 700. The current in the collector can change by a factor of 9 times, nearly 10 times. So, if the load current changes by a factor of 10 and 1, I'm expecting that the collector current will change by that amount, and the VBE will change very little, 50 millivolts, 60 millivolts maybe, by that much, which can be neglected due to the loading effect. But the thing is, will the Zener voltage change too much as a result of load current changing? The answer is no, because your load current does not reflect to drain that node, which it did with the single Zener diode. You remember we connected the load directly to the Zener? Well, we were taking 20 milliamp off of the Zener diode. But here, you're not taking 20 milliamp out of this. You're taking only IE over beta. Maybe 1/100th of that current. So if your load current is changing by 100 milliamp, the base current will change only by 1 milliamp. That's great, because if you were sending 25 milliamp, all of the 25 milliamp goes through the Zener with no load, zero base current. 25, you're deep here in the Zener. Now, if you're putting it or drawing 100 milliamp in this path, your base current is going to change by 100 milli divided by beta, which is like 1 milli. So the base current will take 1 milli off of the Zener assembly. So the Zener current will change from 25 to 24. Fine, that is way safe and well into the Zener stable region. We will not hit that corner. So this pre-regulator will function properly because it will be boosted by the current gain capability of that transistor. But let's see what will happen as a result of changing the current in the emitter. If you change the current in the emitter, which is nearly identical to change of current in the collector, IB will change by delta of IB will be delta of IL, delta of IE divided by beta, and that change will be multiplied. That change should be multiplied by the dynamic resistance of the Zener, which is very small. So whatever delta or whatever the current change there is by 100 milliamp. You want to go from 5 milliamp load to 105 milliamp load current. The base will change by 1 milliamp from its initial value, maybe from 0.05 by 1 milliamp, 1.05. And that change should be multiplied by the change in the Zener resistance, which will be really, really small. So the bottom line is, it is the base current that is facing the Zener, and it can be made pretty small, especially if you select a high beta transistor. The higher it is, the better regulator it's going to be, obviously, because the current will be small. You can do anything you like here. The change will be 100-fold, 150, maybe 250-fold smaller. And it will give you a nicely regulated Zener. But let us take a look at the other aspect of this buffer introduced at that point. When you're taking a current in the emitter path, that current almost entirely comes from the collector path. because IE is almost equal to IC. IE is beta over is 1 plus beta over beta times of IC. Hold on a second. IC is a beta over 1 plus beta times IE. In other words, ICs are like 1% less than IEs, because IEs are a combination of IB and IC. That's why. So, if you're loading in here, the current in the transistor will increase the collector current. But look where that collector current is coming. It's coming from the capacitor. So, the load current that really drains the capacitor, IL here, I will look at the problem in here, kind of by itself. I'm just explaining the details of it. The current in here is in charge of creating the ripple on the capacitor. So the ripple voltage, that fluctuation, which has a negative bearing on the stability of the zener, because it translates to the zener, by many factor reduced. The change in the capacitor voltage, which is changing the collector voltage, will not influence the load voltage. Why? Because when the collector voltage fluctuates, VCE of the transistor will change. But we know that IC of a transistor is independent of VCE. Do you remember those curves? IC and the VCE, the lines were horizontal, nearly horizontal. So if the VCE is changing because of the dropping or rippling collector, the emitter will not change because the current doesn't change. Here, VCE changes, delta IC here. Current doesn't change, emitter current does not change. So the voltage will stay regulated. It will not see the massive ripple on the capacitor. Massive ripple there will reflect on the collector, not on the emitter side. Emitter side voltage will be pretty close to the zener voltage, less by the VB. Of course, it will depend how much current you're drawing, which will cause the VBE to change a little, very little. As I said, if you change that current by almost tenfold, the VBE will change by approximately 50, 60 millivolts, nothing more than that, because of that exponential relationship. Okay, now I'm going to look into the problem with numbers. So this is just explaining the mechanism of that whole thing, how it works. So let us look at the number. Example, here. It says, given that VP is 13 volt peak, VP is 13 volt peak. That's the secondary voltage. Probably VS, RMS, is 13 over radical 13 over radical 2. This is the RMS of the secondary. So remember, in order to convert it into a peak, you take the secondary voltage and you multiply by radical 2. The peaks are higher than the RMS. So that is 13 volt VP. Zener voltage VZ is 5.6. Zener RS is 240 ohm. Beta is 50. And IL max, maximum load current, is 500 milliamp. So we intend to increase the emitter current from very low, practically nothing, a few milliamps, all the way to 500 milliamps. That's a lot of current. Capacitor is 10,000 microfarad, and RZ is 5 ohm. The following can be determined. Number one, first find the average voltage here. The average voltage, which is the centroid of that triangular, is approximately VO peak. So we decide to take the peak. It's close to the top one. So average the center, close to the top. It's just an estimation. It is 13 minus 2 times of 0.7. That allows for diode drop, those two diodes. Okay? IS, which is the current in the resistance RS, is now equal to the average voltage here, which we know it's 11.6, minus 5.6 approximately, the Zener voltage. It's going to stay in the vicinity of 5.6, divided by 240 ohm. So this is like 25 milliamp. So we are biasing, basically. Biasing 25 milliamp. 25 milliamp in that path. So remember that you have a base current in here. IB, which is load current divided by the beta. So IB, which is the IB max, that's the maximum we are going to steal from that node, maximum current we can steal from there. We have 25 supply. That maximum current is going to be approximately IE over beta. It's like saying IC over beta. It's nearly the same. So it is going to be 500 milliamp divided by 50. Beta is 50. 10 milliamp. That's it. So this base current is going to be top 10 milliamp under the highest pressure when you're drawing 500 milliamp. What if you don't draw any current, or you draw 1 milliamp? If you draw 1 milliamp here, you get 1/50th of a milliamp here, nearly like zero, and you're taking practically nothing out of here. All of the 25 will sink into the Zener, will give you a nice steady 5.6 volt. You won't even notice the change in the Zener current. So when it is no load, Zener current is at the max that you're supplying. The 25 will go there. Incidentally, this 25 will permanently stay 25 as long as the current in the Zener is not violated. It's not depleted. It's not withdrawn completely. You leave something in the Zener. Limit is actually IZ max about 5 milliamp. Sometimes 2-3 milliamps. It just depends. So imagine how much we could go. 25. If I want to leave 5 in here, how much the base current can take? Max 20 milliamp. It can go up to 20. 20 that way, 5 here. It's good enough to keep in the zip. Now, if 20 milliamp goes into the base and the beta is 50, the emitter current can be up to 20 milliamp times 50. That's 1 ampere. So this load could go as high as 1 whole ampere. That's 1 ampere power supply. And still, the Zener would regulate. It won't sink below 5.6. So it will be in the steep region, not getting into the horizontal. So that's how to see the things into the circuit. So we got IB equal to 10 milliamp. IZ, therefore, I of Z is equal to IS minus of IB. So 25 milliamp minus of 5 minus of 10, excuse me, 10 milliamp. And this is equal to 15 milliamp. Notice if load was disconnected, then IE would be 0, IB would be 0, and IC would be 25 milliamp instead of 15 milliamp. So that means message is good, 15 milliamp in the Zener, your Zener is regulated. So this is the situation for your Zener. I of the diode, V of the diodes. Here, 25 milliamp, no load, no IE. It goes to here. 15 milliamp, 15 milliamp, IE is 500 milliamp. So that's great. Still, we haven't hit that bend. So that means we are in the steep region, in a good Zener stable region. And as I said, if the line was completely vertical, it never happens. But if it was completely, it wouldn't be an issue. 15 is good. We could go even farther up. Okay, so this is what the Zener current is, 15 milliamp. It is greater than 0, so stays in Zener region. Yes, you have a question?
I don't understand the calculation you did to find VU peak, like the voltage.
V peak? Okay. V peak comes from here. See, that's VP.
Yes.
You lose 0.7 in here, and when it goes through the VO, you lose another 0.7 in this one, then back to the VP. Kirchhoff voltage law.
Oh, that's why you did 2 times 0.7, which is the voltage.
That's why. Exactly. One for this one, the second one for that one. And that was for the positive cycle. For the negative cycle, it's the same thing. It's the negative VP, or just VP. This voltage, that voltage minus this voltage twice. You got it?
Yeah.
Oh, you're welcome. Okay. So, VE is VL, load voltage, and it is VC minus VBE. So, V load voltage in here. Let us assume that under the 500 milliamp, assuming that VBE is 0.7 volt at 500 milliamp. So here, assuming VBE is 0.7 volts at IE equal to 500 milliamp. Since you're doing the calculation for the 500 milliamp, you get 500 milliamp there, you have 0.7 volt in here, so what's the load voltage? 5.6 minus 0.7, that's your load voltage. So VL is 5.6 minus 0.7, 4.9 volts. Okay. This is the load voltage at 500 milliamp, period. So that's it. The load voltage is only affected by one offset, VB offset. Let me keep track of time. 5:30. So I started 5:30. My timings is odd, you know. I begin at 5:30. So I've got 10 minutes. We can make it. So we get 4.9 volts across the load when we have 500 milliamp taking from them. What is taking 500 milliamp? Whatever. It could be an electronic circuit in here. It could be a resistor. Doesn't matter. Now, calculating the ripple voltage. So what will be the maximum current going in this direction out of the capacitor? Which we are going to call that IL average. It's not this load, but it is that current. Let me mark it here. So you will know what is IL. So what color did I use here in this one? IL average. This one is IL average. The DC current that you're drawing constantly from that capacitor. IL average is, there are two paths. Notice, there is one that leads to the collector, so it has got to be collector current, which is almost identical to the emitter current. Next, the current that goes to supply this biasing arrangement, which is 25 milliamp. Okay, so here it is. It's 25 milliamp, that's the IRS, plus the 500 milliamp. Here, plus the 500 milliamp. This is 525 milliamp. Okay. That is the current that is depleting the capacitor. It's causing the capacitor voltage to go linearly down with time. Can we calculate what is the ripple magnitude? This is the formula that calculates the ripple magnitude. Remember, in a full-wave rectifier, those of you who took the 2200 with me, all that detail is there, is equal to IL average. It means the average current that is draining, divided by twice of C times the frequency. Twice of the capacitor times the frequency. Double frequency because there are two cycles in there. IL average is estimated current that drains the capacitor after every peak. So there's a constant taken, that's why capacitor sinks, but rises again, sinks, rises. During that sinking course, that ripple will be created. The size of the ripple will be, this is the ripple, sorry. The ripple is equal to IL average divided by that. I know in the textbooks, basically, to calculate the ripple, they put a resistor here. Well, in many cases, you don't have resistor placed across the capacitor. You don't want to do that. You want to make it useful power supply. So we don't usually put a resistor there. But if there was a resistor, what would be IL average? Guess what? If you had a resistor like R hanging from here to ground instead of that whole circuit, you will take the average voltage of the cap divided by R. So this IL could be substituted by the average divided by R if you had a single resistor connected across the capacitor. But we are applying that to this particular voltage regulator, and that is the governing equation. This is how I estimate my effective current going down, and by dividing by 2CF, it will tell us how much is that ripple it will cause across the capacitor. So you substitute the values for the circuit. There you are, 0.44 volt peak to peak. Great. This is 0.44 volt peak to peak. It's only 3.8% ripple when you calculate it with respect to your average voltage. Here, this is your average voltage. So 0.44 is only 3.8% of the 11.6. So that is how you will calculate the ripple existing across the capacitor. But again, I stress that fluctuation 1 volt will never see light in here. You never see it here. Why? Because that emitter voltage is following the Zener voltage, which Zener is almost free from ripple for the reasons I explained. Their dynamic resistance is very small. That's the whole point. So that 3.8% ripple indeed will be checked, will be stopped because of that transistor stage. Collector voltage can drop, but it will not influence the collector current. The collector current is what you are drawing from the emitter, what your load is drawing at the emitter. Okay, now regulation. Okay, here it is. Ripple. How much ripple do we anticipate we will get at the output? Think about it this way. VZ minus VBE is equal to V, let's say VL. VL is this voltage here. VL. If VBE can be assumed to be constant during this ripple fluctuation, then delta VZ is the same as delta VL. In other words, ripple at the Zener is going to be identical to ripple at the emitter. The offset is fixed. You're drawing 500 milliamp, it's a 0.7 fixed, okay? So if the base fluctuates a little, then load voltage fluctuates with it, exactly identical. Guess what? We know how much is the delta VZ. The change at that corner to the RS and the dynamic resistance translates into RZ times VR over RS plus RZ. This is the ripple at Zener or load. They're identical, assuming that VB doesn't change. So guess how much it is. RZ is 5 ohm over 240 plus 5 multiplied by 0.44. So the ripple is only 9 millivolt peak to peak. This is fantastic. Here getting a 4.9 volt regulated voltage only with 9 millivolt residue on it. It will not see the 440 millivolt residue here, the main ripple at the collector, because collector has no connection to the emitter. Collector can play, emitter can stay solid. VC will change, but VC change does not cause IC to change. So the circuit reduced the ripple. And the reason that you see just a tiny bit is because of the Zener resistance. If you could silence the Zener, ripple in here, that would be fantastic. That would be great. One solution would be get a R and a Z that biases a second R and a Z and get the reference voltage from the second Zener. It's Zener regulating a Zener. You see double Zener regulation. Then feed the transistor. You can reduce this maybe tenfold to 1 millivolt peak to peak.